Hi everyone, I'm Grisha, a PhD student in Tel Aviv University, and I'll talk about the extremely variable AGN and the changing look AGN and the host galaxies in SDSS 5. The work I've been doing many testing board groups and many other members from the Black Mapper team in SDSS 5. Okay, so first of all, changing look AGNs can mean different things depending on the spectral regime. In the X-rays, it means transitions between obscured and unobscured states. In UV optical, in the most extreme case, transitions between type 1 and type 2 AGNs, and I'm going to focus on objects in the UV optical. So formally, the definition of changing look AGN, as you've heard this morning, is objects that show the appearance or disappearance of broad emission lines and the quasi-like continuum, like the object you see here before, or the blue continuum and the Balmer lines almost completely disappeared over a decade. These are usually identified in repeat spectroscopy surveys, so with cadence of a few years. There are, I think, about 1,000 sources reported in the literature so far. And as was mentioned this morning, they also provide an opportunity to study the relation between the AGN and the host galaxy, just by virtue of having observations of the same system, once in an AGN dominated and once in host. And I've listed here a few of the open questions or challenges and reasons why changing look AGN are interesting, in my opinion. So as we've heard this morning, they are challenging for standard accretion disk models, because if we interpret this variability as changes in the accretion rate, then the relevant time scale is the viscous time scale, which is much longer for standard accretion disks than what we observe. There's the open question of the connection, possible connection to the host galaxy's properties and this phenomena. Whether these rare events matter in the big picture of supermassive black holes. There is a challenge of multi-wavelength observations. So ideally, if you want to understand these extreme changes, you would like to have multiple observations during the transition itself, and this is very challenging. And there's also a point of the biases and missing populations. I would come back to this point toward the end of my talk. And the connection to normal AGN variability. We know that all AGN vary. So is what we see just the extreme tail of normal variability, or is this some other kind of physical phenomena? I'm not really going to answer these questions, just address some of them in my talk. So I'm not going to go into details, specific models of changing look AGN events. I think we will hear more about them in the upcoming days. So broadly speaking, we can think about them either as some variations in the accretion flow, or some variations, nothing actually happening to the accretion flow, but some variations to the obscuration, where, for example, material passes through our line of sight. So far, the consensus, I think, in the literature is that variable accretion flow probably explains most of the sources. For several reasons. I'll mention some of them in the next slides. So our goal was to conduct a large statistical study of a sample of changing look AGNs, and we have obtained this sample using the Black Hole Mapper program in SDSS 5. So SDSS 5 is an all-sky survey that obtains a spectroscopy in the optical using the Bose spectrograph. In the first year, it uses plate data, and then it switched to fiber positioning system. To this day, it has obtained a repeated spectroscopy of over 100,000 known AGNs. So these are AGNs with spectra in legacy Sloan, and this allows us to probe time scales from up to 2 decades and down to hours when we look at the RM fields. And here at the bottom, you can see the design of some of the Black Hole Mapper programs that obtained a repeat spectroscopy in the northern sky. So just using the first year data, we have obtained over 100 changing look AGNs. Our automated search relied on detecting extreme borderline variability, complemented by visual inspection. Our sample probes timescales from up to 2 decades and down to 2 months in the most extreme case. Most of them are tone-off objects, But this is expected because we are coming back to things that were already cataloged as quasars in SDSS. So in our paper, we show that this is consistent with actually a 50-50% turn off and turn on rate. We also conducted an extensive effort of independent follow-ups and photometric cross matches just to make sure that what we see are actual real changes, not calibration issues. And we also discovered about 88 other extremely variable AGNs that were not classified as change in look. And I would come back to these objects at the end of my talk. So here I'm just showing two examples. On the top, we see an object that has brightened across 2 decades. At the bottom, an object that dimmed. Here's another example. So this object shows less dramatic variability, but it demonstrates that when you have more than 2 spectra, you can actually sometimes resolve the different component, how different components of the AGN change in these events. So if we zoom into the quasar continuum at the Balmer lines, we can see that the quasar continuum dimmed somewhere between 2010 and 2017. Balmer line also somewhat dimmed in this period, but the H alpha line didn't respond at all and actually dimmed only later by 2020 when it was observed in SDSS 5. It seems to lag behind H beta. I'm not sure what the explanation for that is, so I'd be happy to hear any ideas if we have any after the talk. So our large sample allows us to do some statistics. So the first thing we did is to look at the change in look AGN fraction. So this is just the number of change in look AGNs that we observed divided by the total number of SDSS5 AGN with repeat spectroscopy in different luminosity, black hole mass, and Eddington ratio bins. So in the middle panel, we can see that we don't see any strong trends with black hole mass. I think that this favors tidal disruption events as the driver of the changes that we see. But we do see trends with luminosity and the Eddington ratio. We see that as the properties increase, the change in look fraction decreases. And the total rate that we find for our change in look AGNs is about 0.4%, or 1.2% if we consider only sources with redshift lower than 1. And this of course is a lower limit because we might have missed some objects. So we see here trends with luminosity and Eddington ratio, but to see which one of these properties has the more fundamental relation to the change in look phenomena, we need to do a more careful analysis. So what you see here on the bottom left is the comparison between the distributions of Eddington ratios of AGNs and a control sample that was matched in volumetric luminosity and redshift for our change in look AGNs. And you can see here that even when matching for luminosity, we still see that distribution of Eddington ratios of change in look AGNs is lower in a statistically significant manner. But when we do the reverse exercise, which you can see here on the right, now we match for the Eddington ratio and the redshift and compare the volumetric luminosities on the top and the black hole masses in the bottom. We don't see a statistically significant difference between the distribution. And this hints that it is the Eddington ratio that has the more fundamental relation to this phenomena rather than the volumetric luminosity. And again, the fact that we don't see any difference in distributions of masses, this favors tidal disruption events as the driver of the changes that we have. Okay, so I want to move now to beyond statistics to an individual case. This is one of the most extreme cases, the case extreme change in look AGNs in terms of timescales that we have observed. So it has 2 archival spectra, a bright Sloan spectrum from 2001, and it was reobserved in 2016 by McLeod et al. And in SDSS5, it showed an even dimmer state with the H beta line and the quasar-like continuum significantly dimming. We then followed up on the source 2 months later, and it brightened back to almost exactly the same state it was in before. And the transient nature of this transition was also captured in ZTF photometry. You can see here a relatively steady light curve with a dip of about 1 magnitude in the ZTF G band. So these SDSS5 spectra were taken by coincidence exactly at the bottom of the dip, and the first follow-up spectrum is taken right when the light curve recovered. So this just the shape of the light curve taken together with the fact that the spectral changes that we see can be modeled, can be explained by advanced reasoning, made us consider that maybe this is a case of variable obscuration rather than variable accretion. The problem with this explanation is that this is requires a large obscurer size that can obscure a significant fraction of the BLR. Also, the obscurer velocity that we get is very high. You can get this if you consider the typical size of the BLR for such objects. In just the short time scale of the transition, we get a velocity of half the speed of light, which is unreasonable. And also the wise light curve, which I would show in a moment. So after publishing the paper, we've continued to monitor the source. This is the updated light curve. So this is the original dip. And you can see that there was another recent dip in the light curve, but it's a smaller one. And the source generally exhibits some weird variability. But the most interesting thing is that you can also see a dip in the wise light curve. And the dip in the wise light curve is delayed by about 2 months when compared to the optical, is what you would expect from an accretion-driven event. And this is inconsistent with variable obscuration. So probably some kind of something of the accretion flow. The accretion flow changes explain this object, but we still don't know what explains this particular shape in the light curve. Okay, so I mentioned in the introduction that there's an open question of whether there's a connection between the host galaxy properties and changing AGN events. So to address this question, we have obtained follow-up high-resolution spectroscopy using the X-shooter and GMOS for a subset of dimming changing AGNs from our larger sample. And you can see here one such example. Again, the archival spectra is in blue from 2000. By 2021, it dimmed to a dim state. And this is the red spectrum, and in black you see the X-shooter spectrum, which, as you can see, confirms that the object is still in a dim state. But when you look more closely at the spectra, you can see several interesting things. First of all, we see that the lines continue to dim, the H-beta line disappearing. We also see a broad magnesium line even in the dim X-shooter state, which again disfavors obscuration because the UV magnesium 2 line should be affected by obscuration much more than the optical boundary lines. And finally, because the source is host dominated, we can now study the stellar absorption features in a way that wasn't possible before. So this is exactly what we did. So first we checked where changing AGNs fall on the M sigma relation. And what I'm showing you here are preliminary results. We still didn't finalize our analysis. We didn't look at all the spectra that we obtained. So we obtained the black hole mass from the bright state using H alpha single epoch prescriptions and the stellar velocity dispersion using PPXF. You can see one feed from PPXF here on the left. The gray regions are the regions that we are masking because even in the dim state, there is still some AGN contamination. You can see in the residuals on the bottom some emission lines. And then we place our objects on the M sigma relation. So the dashed line that you see is the Corminian-Hoare best fit for elliptical galaxies and classical bulges. And then we fit our objects and fix the slope to the same value from Corminian-Hoare. And we get a systematic offset of about 0.3 dex. Means that the masses that we get from the variable prescriptions are lower than the masses you would expect from a Corminian-Hoare relation. So we're still working on explanations of what we see. It might be due to some systematics in the way we measure the black hole mass or the velocity dispersion, or maybe some systematics in the Corminian-Hoare measurement. But if the changing AGNs are indeed there, this might be maybe due to some evolutionary processes where changing AGNs or AGN in general are lagging behind in growth behind the host galaxy. So next we look at the stellar mass and stellar age plane. So we obtained the stellar mass and stellar age using Firefly, which is a code that fits a combination of single burst stellar population models to our spectra, and we compare them to a catalog that uses the same code for type 2 AGNs here on the right, and for star-forming galaxies on the left. As then you can see on the right, except for a few outliers, we're generally consistent with the general AGN population. And in addition to that, when we inspect the stellar populations, we see no evidence for recent starburst in our change in look AGN sample. Next, we can look at the star formation rate versus stellar mass plane. So again, stellar mass was obtained using Firefly. For the star formation rate, we use an O2 estimator that was calibrated for AGN. And we compare star forming galaxies on the left and the AGNs on the right. And again, we see that we're broadly consistent, except for a few outliers that we need to inspect with the general AGN population. So I guess in terms of the basic stellar properties like stellar mass, star formation rate, and stellar age, we don't see any difference between changing look AGNs and the general agent population, but we do need to be more careful here. We're not doing any matching here. We can do maybe some more careful matching between our changing look AGN properties and the agent properties to see if we can get to refine these results. Okay, so the last thing I want to talk about is just a question about the difference between what we call changing look AGNs and extremely variable quasars, and is there any difference between them? So here on the top, you would see what we would classify as a change in look AGN. And we classify this as a change in look AGN because in the dim state, the broad edge beta line disappeared. On the bottom, we see an object that shows also extreme variability, as you can see, but in the dim state, we see a broad edge beta line. So this was a type 1, even in the dim state. We would just call this an extremely variable quasar. Maybe move on. But the underlying phenomena can be the same, just changes in accretion rate. So if you consider a very simplistic model, so here I'm showing you 3 fake spectra with a constant host component and just AGN emission, constant host component and AGN emission of different strengths. So each time I'm increasing the AGN emission by a factor of 3. So if you would have observed the bright state and the intermediate state, you would call this an AVQ. If you would observe the intermediate state and the dim state, you would call this a change in look AGN because the broad edge beta seems to disappear. It's not actually disappearing, it's just that because of the contrast with the host galaxy, you're not able to detect the broad line. So if indeed the phenomena to look is just continuous changes in accretion rate and not some binary transitions, and we choose to analyze only change in look AGN events, we might introduce biases to our samples. Now, I don't think that this explains that all change in look AGN events. I think that we would hear during the next days about events where broad lines actually seem to appear, but I think this is relevant for many objects in the literature and something that we should keep in mind. So to summarize, so from the first year of SDSS 5 data, we have found over 100 change in look AGNs with an observed fraction of about 1% for redshift lower than 1. These show preference for relatively low Eddington ratios and no dependence on black hole mass or luminosity. We're controlling for the Eddington ratio. Some of the changes can be recurring and happen on timescales as short as the 2 months. And when it comes to the host galaxies of change in look AGNs, we find that change in look AGNs appear to lie below the Corrigan-Hall relation by about 0.3 dex. But that in terms of stellar mass, stellar formation rate, and stellar age, we so far didn't find any evidence of any difference between change in look AGNs and the AGN. And finally, the change in look AGNs don't show any evidence for recent starbursts. Then that will be it. Thank you for
So the source with the really nice light curve for the for many many years. I'm curious for the wise observations. Yeah, this one. Was there any evidence for changing the color between the wise observations though?
So we didn't look at the color actually. But we didn't check the color.
And I'm assuming there is no wise 3 and 4 as delta pi.
Yeah. And also no X-rays and fire.
Have you checked the latest data release from WISE to see if the third or the second so visible there? Because now you can get August the campaign.
I think, yeah, I should check that. I think that this is the recent WISE data that I could get. Yeah, we need to look at it.
Related, I was actually able to ask the same. So for this SDSS sample, instead that you had observations with CTF and WISE also. Have you checked color variations? Because I think this is probably what can help us to identify the sources.
So we mainly looked at I guess we mainly looked at trying to identify whether we actually see the transition in the WISE light curve, and for many of the objects we actually did see the transition also in the WISE light curve. Some objects we didn't see that, so I guess these kinds of objects definitely cannot be explained by variable obscuration, but we didn't look at the colors. That's an interesting idea.
Benny and I were talking at the break about the biases and the turn on and turn off. More to say about 65% turning off and 35% turning on. How likely it is you're able to see each of those.
So there's a work by Shen that looks at these biases. When you come back to quasars, you expect to be biased towards like winning events. We did find that our functions are, we cannot prove that it's actually intrinsically 50-50, but it's consistent with an actual function, intrinsic function of like 50-50.
If I can comment on that, I think it's the bias of the selection with the spectroscopy, and you have the opposite bias probably in photometry because it's easier to see a turn on. So that's why we need to combine selection to have a more complete.
There's a question on Zoom.
Yeah,
Hey, thank you for these interesting results. So since you have M star as well, have you created the black hole mass stellar mass relation, and how does it compare to M sigma? Because the problem with sigma, of course, is that these are fiber-based spectra, so that could, depending on the morphology and the distance, could influence your sigma. And from high redshift, we've heard that there are differences between M sigma and black hole mass stellar mass relation. So just curious if you looked into that.
Well, not yet. It's something we plan to do. I thought about this yesterday, but I decided to not create a new plot in the last moment. And this is actually not a fiber. This is a slit actually, because this is the actual spectra. But I guess that this also can introduce maybe some systematics in the sigma measurement. But yeah, the next thing we would look at is the stellar black hole mass versus stellar mass.
Thanks.
Last questions. Yeah.
Remember, I have a question about this one. For me, it's not clear the one on the right side. You have this. Your fit is the gray.
Yeah, no, my fit is the solid black, and the gray region is just the uncertain.
Obtained from the red.
From the red, yeah, from the red point, which is our change in AGNs.
Because the error bars are huge.
Yeah, well, okay, I put it in, yeah, the error bars are big, this is the, yes, but they do lie systematically below the comedian horse, so I think that this is 11 forces below compared to 2 above. But yeah, I guess that, you know, when we analyze the entire sample, I hope we'll get like better statistics.
The gray area includes the error bars.
This is with a fixed slope.
Yeah, this is the big slope. We also did like a free slope, but then the slope is not constrained that well. That's why I'm not showing it yet. But yeah, like for individual source, you cannot say anything. Just I'm showing here that's the 0.5 dex uncertainty for black hole mass measurements. But yeah, with a large sample, we can tell if there's some kind of systematic effect, assuming you do trust the stellar velocity dispersion measurement.
I don't know if you have compared these measurements. I don't know, but this is, sorry, it's temporary. Yeah, because I was wondering if with SCD analysis you can just compare the results, but this is for
The analysis, what do you mean?
no, sorry. Well,
Let's, again. Right, last speaker,